For generations, astronomers believed they had a reasonably clear picture of how the universe evolved after the Big Bang. According to the best available models, the first galaxies formed slowly. Tiny clouds of gas collapsed under gravity, creating the earliest stars. Over hundreds of millions of years, those small systems merged together, gradually growing into the large galaxies we see across the cosmos today. It was a logical story supported by decades of observations. Then the James Webb Space Telescope began looking deeper into space than any observatory before it. Because light takes time to travel across the universe, looking farther into space also means looking farther back in time. Webb's powerful infrared instruments allow astronomers to observe galaxies whose light has traveled for more than 13 billion years, revealing what the universe looked like only a few 100 million years after the Big Bang. Scientists expected to find small, faint and relatively simple galaxies. Instead, they found something unexpected. Hidden within Webb's deepest observations were galaxies that appeared surprisingly bright, surprisingly massive and remarkably well developed for such an early period in cosmic history. Rather than slowly taking shape over billions of years, some seem to have assembled much faster than existing computer models predicted. These observations immediately captured the attention of astronomers around the world. Not because they disproved modern cosmology, but because they suggested that important details about the early universe were still missing. Every unexpected galaxy became another clue that the story of cosmic evolution might be more complex than previously believed. To understand why this discovery matters, it's important to understand how Webb observes the universe. As space expands, light traveling across billions of years is stretched toward longer wavelengths, a phenomenon known as redshift. Visible light emitted by the earliest galaxies gradually shifts into infrared wavelengths before reaching Earth. This is precisely the type of light the James Webb Space Telescope was designed to detect. By capturing these ancient infrared signals, Webb allows astronomers to study some of the first generations of galaxies ever formed. In many ways, the telescope functions like a time machine, showing us the universe during its earliest chapters. What surprised researchers was not simply the existence of these galaxies, but their apparent maturity. Some appeared richer in stars than expected. Others seemed brighter than computer simulations had predicted. Their structures suggested that galaxy formation during the first few 100 million years after the Big Bang may have progressed much more rapidly than earlier models suggested. That raised several fascinating possibilities. Perhaps early galaxies formed stars with extraordinary efficiency. Perhaps clouds of gas collapsed faster than scientists had assumed. Or perhaps the methods used to estimate the masses and distances of these galaxies still require refinement as more observations become available. Every possibility remains an active area of research. One point, however, is especially important. These discoveries do not show that the Big Bang theory has failed. Instead, they demonstrate exactly how science progresses. Observations reveal unexpected details, researchers improve existing models, and our understanding becomes increasingly accurate over time. The foundation remains strong, while individual pieces are refined as new evidence appears. History shows this process again and again. New planets, black holes, dark energy and countless other discoveries have expanded scientific understanding without discarding everything that came before. Each breakthrough added another layer to humanity's picture of the universe. The James Webb Space Telescope is continuing that tradition. By observing galaxies farther away than ever before, it is revealing that the early universe was likely a far more active and dynamic place than astronomers once imagined. Rather than a quiet period of slow growth, it may have been an era filled with rapid star formation, energetic galaxies and surprisingly complex cosmic structures. And that realization is opening an entirely new chapter in our understanding of how the universe evolved. As astronomers continue to analyze Webb's observations, attention has shifted from simply discovering these ancient galaxies to understanding how they could have formed so quickly. The answers may reshape important details of cosmic evolution, while leaving the overall picture of the universe remarkably intact. One possibility is that the earliest galaxies were incredibly efficient at turning gas into stars. In today's universe, star formation is often slowed by stellar winds, supernova explosions, and complex interactions between gas and dust. But conditions in the young universe were very different. Vast reservoirs of pristine hydrogen and helium may have collapsed rapidly under gravity, creating intense bursts of star formation within a surprisingly short period of time. Another question concerns the appearance of the first supermassive black holes. Several distant galaxies observed by Webb seem to contain enormous black holes far earlier than many theoretical models predicted. These objects may have grown from unusually massive, seed, black holes, or they may have experienced periods of extremely rapid growth fueled by enormous quantities of surrounding gas. Researchers are now investigating multiple possibilities, each offering new insights into how galaxies and black holes evolved together during the universe's earliest ages. Chemical composition also provides valuable clues. When stars live and die, they create heavier elements such as carbon, oxygen, silicon, and iron. Finding these elements inside very distant galaxies suggests that multiple generations of stars may have formed, evolved, and exploded far earlier than scientists once expected. That means stellar evolution itself may have progressed at an extraordinary pace shortly after the Big Bang. At the same time, astronomers remain cautious. Observing objects at extreme distances is incredibly difficult. Their light is faint, stretched by cosmic expansion, and influenced by gravitational effects along its journey to Earth. Small uncertainties in brightness, distance, or mass can significantly affect scientific interpretations. As Webb continues collecting additional observations, researchers are refining their measurements to determine which early galaxies truly challenge existing models and which can be explained through improved analysis. This careful process is one of science's greatest strengths. Every surprising observation is tested repeatedly. Independent research teams analyze the same data using different methods. Computer simulations are updated, predictions are compared with observations, and conclusions are revised only when supported by strong evidence. Rather than weakening scientific understanding, this process makes it increasingly reliable. The discoveries made by the James Webb Space Telescope demonstrate that the universe still has the power to surprise us. Every deep field image reveals thousands of galaxies, each representing a different chapter in cosmic history. Some existed when the universe was only a few % of its current age, offering direct evidence of events that occurred more than 13 billion years ago. Looking at these galaxies is unlike looking across space. It is looking backward through time itself. Every photon collected by Webb began its journey billions of years before Earth even existed in its present form. Those ancient signals have traveled across expanding space, surviving encounters with galaxies, gas clouds, and gravity before finally reaching a telescope built by human hands. That connection is extraordinary. For the first time in history, humanity can directly study the earliest generations of galaxies with remarkable detail, transforming distant points of light into laboratories for understanding the birth of the cosmos. Future observatories will push this exploration even further. Next-generation ground-based telescopes and upcoming space missions will work alongside Webb, measuring the masses, motions, and chemical compositions of even more distant galaxies. Together, these instruments will help answer some of astronomy's greatest questions. How did the first stars ignite? How quickly did galaxies assemble? And what processes shaped the universe into the vast cosmic web we observe today? Perhaps the most important lesson from Webb's discoveries is that the universe is still teaching us. Each unexpected galaxy, every unusual spectrum, and every refined measurement reminds us that scientific knowledge is always evolving. The goal is not to prove old ideas wrong, but to build increasingly accurate explanations based on the best available evidence. The James Webb Space Telescope has opened an entirely new window into cosmic history. Through that window, humanity is witnessing a universe that is richer, faster, and more dynamic than previously imagined.